this episode, we focus on a simple truth that surprises many beginners. AI systems do not fail only because the model is weak. They often fail because the data is weak. When people imagine an AI project going wrong, they picture a technical glitch or a scary cyber attack. But a huge percentage of problems start much earlier, when the data is incomplete, inaccurate, inconsistently labeled, or impossible to trace back to its source. If you validate data quality early, you prevent a lot of downstream chaos, because data mistakes become model mistakes, and model mistakes become real-world harm. Early validation is also cheaper, because fixing data before it spreads through training, tuning, and deployment is far easier than fixing behavior after users are already relying on the system. Our goal is to make 4 words feel practical: completeness, accuracy, labeling, and lineage. Completeness is about whether the data covers what you think it covers. Accuracy is about whether it reflects reality. Labeling is about whether the meaning assigned to data is correct and consistent. And lineage is about whether you can trace where it came from and how it changed. When you can hold these 4 ideas in your mind, you can spot quality risk before it turns into an AI failure. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Let's start with what data quality means, because beginners sometimes think it is only about removing duplicate rows or obvious errors. Data quality is about fitness for purpose, meaning the data is good enough for the specific job you want the AI system to do. A dataset can be clean in a technical sense and still be low quality for a particular use case if it is missing key populations, missing key situations, or reflecting outdated conditions. Data quality also includes consistency, meaning the same concept is represented the same way across the dataset, and it includes clarity, meaning you know what each field or example actually represents. In AI work, quality is not only a database issue, it is a risk issue because low-quality data can cause unfair outcomes, unreliable performance, or unsafe recommendations. Another important idea is that data quality is not fixed because pipelines and sources change over time, so quality can drift if nobody is watching. That is why early validation is framed as a discipline, not a one-time cleanup. When quality is validated early, you build a foundation that makes later testing and monitoring meaningful. Completeness is the first major concept, and it is about whether the dataset includes the pieces needed to support the system's purpose. Completeness can mean simple things like missing values, but in AI risk work it often means missing coverage. For example, if you build a system meant to help a wide range of users, but your dataset mostly reflects one type of user, then the system can appear to work while quietly failing for people who are underrepresented. Completeness also includes scenario coverage, meaning the dataset includes the range of situations the system will face, including edge cases and unusual but realistic conditions. Beginners sometimes assume that more data automatically creates completeness, but you can have a huge dataset that still misses important cases if collection is biased or limited. Another completeness issue is time, because data can be complete for last year's reality, but incomplete for today's reality if conditions have changed. Validating completeness early means you ask what the system will face, then you check whether the data truly reflects that world. If the answer is no, you fix the gap before the model learns the wrong world. Accuracy is the second concept, and it is about whether the data represents what actually happened or what is actually true. Data can be inaccurate because of human error, system error, measurement limitations, or even incentives that cause people to record things in a distorted way. For example, if workers are pressured to close tickets quickly, the recorded resolution categories might be chosen for speed rather than truth, which makes the dataset inaccurate for learning meaningful patterns. Accuracy problems can also appear through stale data, where the information was true when recorded but is no longer true now, which matters if the AI system uses it to make current recommendations. Another accuracy problem is mismatched definitions, where different sources mean different things by the same label, such as what counts as urgent or what counts as resolved. Beginners often think of accuracy as a simple percent correct, but accuracy is often messy because reality is messy. Validating accuracy early means checking how data was generated, whether the process encourages honest recording, and whether definitions are consistent. If you cannot trust the accuracy of the data, you cannot trust the behavior of the system trained on it. Labeling is the third concept, and it deserves special attention because labels are how humans teach the system what is correct. Labels might be categories, ratings, outcomes, or annotations, and in many AI systems, labeling is the difference between a model that learns the right lesson and a model that learns a distorted one. Labeling problems often happen because people interpret categories differently, because instructions are unclear, or because the label set does not match the real complexity of the situation. A beginner-friendly example is sentiment labeling, where one person calls a message negative because it contains frustration, while another calls it neutral because it is polite overall. If labeling is inconsistent, the model receives conflicting teaching signals, and it can become unstable or biased. Another labeling risk is hidden value judgments, where labels reflect the labeler's assumptions rather than objective reality, which can embed unfairness. Validating labeling early means ensuring there are clear definitions, training for labelers, and checks for consistency across labelers. If labeling is treated as a minor task, it becomes a major source of downstream risk. A closely related beginner concept is that labels can be wrong even when they are consistent, because consistency is not the same as correctness. A team can consistently label customer complaints as user error to reduce internal workload, which creates a consistent dataset that teaches the model to dismiss real product problems. This kind of systematic mislabeling can create harmful recommendations, especially if the AI system influences decisions about support, refunds, or escalation. Another example is when labels reflect past decisions that were biased or flawed, meaning the dataset encodes historical injustice, and then the model learns it as if it were truth. Early validation includes asking not only are labels consistent, but also do labels reflect a fair and accurate representation of what should happen. Beginners sometimes think AI is objective because it uses math, but labeling is one place where human judgment directly enters. If you validate labeling early, you can catch these distortions before they become automated behavior. This is one of the reasons data quality is inseparable from ethics and fairness. The data teaches the system what the organization values, whether the organization realizes it or not. Lineage is the fourth concept, and it is about traceability, meaning you can track where data came from, how it moved, and how it was transformed. Lineage matters because when something goes wrong, you need to know what influenced the system's behavior. If you cannot trace a dataset back to its sources, you cannot confidently answer questions like whether personal data was included, whether the data was authorized for this use, or whether a particular subset was corrupted. Lineage also matters for reproducibility, meaning you can rebuild the dataset or at least explain what it looked like at a specific point in time. For AI systems, lineage can include transformations like cleaning, filtering, tokenization, or feature extraction, and each transformation can change meaning. Beginners sometimes think lineage is only a compliance requirement, but it is also a debugging requirement and a safety requirement. Without lineage, you cannot prove control and you cannot improve intelligently after failures. Validating lineage early means confirming that records exist for sources, transformations, and versions, so you are not building on a mystery pile of data. When you put these four ideas together, you get a powerful early validation mindset. Do we have enough of the right data? Is it true enough? Is it labeled in a way that teaches the right behavior? And can we trace it? The reason this should happen early is that every later stage depends on it. If completeness is poor, testing results will be misleading because tests will not reflect real conditions. If accuracy is poor, you might optimize the model to match errors rather than reality. If labeling is weak, you might mistake noise for signal and then deploy unstable behavior. If lineage is missing, you might not be able to answer basic questions about what the system learned from and whether the learning was appropriate. Early validation also supports privacy and security, because knowing data origins helps ensure you have permission to use it and helps detect unauthorized or suspicious sources. Beginners should remember that quality problems are not just technical debt, they are risk debt. The interest on risk debt is paid by users, by trust, and sometimes by legal consequences. Another useful part of early validation is learning how data quality connects to bias and fairness, because those topics often feel separate to beginners. Bias can come from incomplete representation, which is a completeness problem, such as when certain groups are missing or underrepresented. Bias can also come from measurement choices, which is an accuracy problem, such as when a proxy measure does not reflect the real concept. Bias can come from labeling decisions, which can embed assumptions and stereotypes. Lineage matters here too, because if you cannot trace sources, you cannot evaluate whether the dataset includes problematic origins. Early validation does not guarantee fairness, but it creates the conditions where fairness can be evaluated meaningfully. If you skip early validation, fairness testing becomes unreliable because you do not know what the model learned from and you cannot explain why it behaves the way it does. This is why data quality is a foundational risk control rather than a nice-to-have. When you validate early, you also create transparency, which makes later conversations with stakeholders more honest. It is also important to address the misconception that you can fix data quality problems entirely with model cleverness. Some people believe that bigger models or more advanced techniques will overcome bad data, but garbage in still becomes garbage out, even when the system looks impressive. A model can smooth noise, but it cannot reliably invent missing reality, and it cannot correct systematic mislabeling without additional signals. Another misconception is that data quality is only the data team's problem, when in reality product choices determine what data is collected, and governance choices determine what is allowed, and security choices determine what is protected. Early validation works best when it is shared, meaning the people who understand the domain help define what good data looks like. A final misconception is that validation is slow and blocks progress, when in reality it prevents false progress that will be undone later. The cost of launching a system based on weak data is often paid later in rework, incidents, and lost trust. Early validation is how you avoid that trap. As we close, validating data quality early is one of the most practical and high-impact habits in AI risk management because it prevents subtle problems from becoming automated harm. Completeness asks whether the dataset covers the real world the system will face. Accuracy asks whether the data reflects reality rather than errors or distortions. Labeling asks whether the teaching signals are correct and consistent. And lineage asks whether you can trace sources and transformations to maintain control. When these four areas are strong, testing and monitoring become meaningful because you are building on a trustworthy foundation. When they are weak, everything else becomes guesswork, no matter how advanced the model appears. For brand new learners, the key takeaway is that data is not just input, it is an engine of behavior. If you want an AI system that is safe, fair, and reliable, you start by validating the data early, before the system learns the wrong lessons, and before those lessons reach real people.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.